All right, so it's now recording. Okay, and let's just start the Jupyter Notebook. Okay. All right, so we are ready to start talking about GANs. The GAN means generative adversarial network. Okay. So let's start the Jupyter here. That. So let's call this a simple binary GAN. Okay. All right. So we will use a lot of the code that we've used in class before, right? And it'll be very object-oriented. And as I've been saying for a while, doing things in a very object-oriented approach makes it easier now that we start to look at very advanced or the more advanced algorithms, okay? So that's going to be familiar. All right, so the GAN stands for generative adversarial network. Okay, so think about that. Generative just means that it creates things, right? Adversarial means there's some kind of competition, and network, well, it's neural networks, right? So the generative, what does that mean exactly? What do neural networks do? Neural networks have inputs and outputs, right? What is the input usually? Some kind of a vector of dimension d, right? And what is the output usually? So far, it's been a vector. Sometimes it was a vector of one neuron. In the last example of CIFAR 10, it was a vector of size 10, right? But think about this. Think about this. We can have a vector of size 784, an output vector of 784. And if I have a vector of size 784 and I unspaghettify it and make it 28 by 28, I effectively have an image. Do you see that? So that's what we're doing here with a GAN. Our GAN basically produces vectors. That's the generative part, except that now the vectors are not like CIFAR where we had all zeros and then one thing was a one, right? Now we can have a vector of size 784 where we actually estimate the value for each one, right, of those cells in that vector of size 784. And then if we follow a specific logic, we can generate those values to be an image, like a 7 or a 6 or a cat, whatever it is. Do you guys see that? So that's it. That's kind of the idea, okay? So today, my generative model for this binary approach is just going to generate vectors of size 4, right? But it's the simplest thing. We're not going to use data. Instead, we're just going to use our data that we have to read in from somewhere. And instead, we're just going to generate our data automatically. So it should be very, I like this example actually for the GAN. So a lot of it hopefully will be straightforward. And then there will be some parts. There is one part that's a little bit tricky to understand. Okay. So another important thing about GANs is before we've always had just one neural network. Always. This time around, however, we have two. And they're playing a game against each other. So it's really the idea comes from game theory, where now you have two agents with different objectives and different goals. Do you see that? And so this is what we're going to be building. So we need to build two neural networks. But because we take an object-oriented approach, we're just going to create a class called generator and a class called discriminator. We're going to instantiate them, and then these two are going to compete against each other. Does that make sense? That's what a GAN is. A GAN is two neural networks with different loss or objectives, basically. Okay. So who came up with this idea? This idea was it was basically proposed in 2014 by Ian Goodfellow. This is like, there's some discussion that this idea was present way back in the 90s and things like that, but that's true of just about everything in engineering and science. And so the key thing is that Ian Goodfellow with neural networks made it work, right? And made it be an effective thing to be used. Jean LeCun said that, you know, sometime in 2017, that it was the best idea in AI in the last 10 years. 3 years later, in 2017, we got the Transformer paper, Attention is All You Need. So it was pretty short-lived. That's a great idea. So, and now it's been 6 years since Attention is All You Need, and we haven't really gotten a new algorithm in deep learning, at least that I'm aware of. And so, yeah, that's kind of where it is. All right, so anyway, this is the idea. So now let's get into the code. The code should be familiar. And we're going to train this binary thing, right? So we're going to basically create vectors that are binary. 1, 0, 1, 0 is the pattern. So I can initially create a vector that creates ones and zeros, but it's random. So I can have all zeros, all ones, 0, 0, 0, 1, 1, 0, 0, you know, those are random sequences. My goal is to build a neural network that generates, that's why it's generative, vectors of size 4, but the pattern is always 1, 0, 1, 0. Does that make sense, guys? Is that clear? Any questions? Nope. All right, so that's it. I mean, it's to me in GANs, in the GANs space, it's the easiest example I've seen, and I really like it for that purpose. So hopefully it'll make GANs very understandable so that you can apply them. So let's go ahead then and get started. So like I said, I'm just in the interest of time, right? I'm not going to type up all of this. Instead, we're just going to copy the code and I'll explain it from my GitHub. So we've got our libraries, torch, NN. We're going to take an object-oriented approach. So we're going to instantiate torch NN classes. We're going to use pandas, matplot, NumPy, basically. It's the basic libraries that we've been using. Then here, this is the first example of what we're going to be doing. So I'm going to add this function here. Okay, so this is the function that generates real data. Okay, so this is for now. If I wanted to generate patterns that are 1, 0, 1, 0, I can just write that code, right? And it does it. However, what I want is a neural network, right? That does that for me, not, you know, heuristically generating such as that. All right, if you look at this function, generate real, what it is something that should be very familiar to you already. You create a torch tensor, which is float, right? And we assign it to a variable real data. And notice it's got 4 values in it. So we call random uniform. And so it's going to generate values between these ranges. So the first value is going to be from 0.8 to 1. The next value is going to be from 0 to 0.20. The next value, 0.8 to 1. And the next value, 0 to 0.2. So why am I not generating just specific values? Because usually we have noise in the data, right? The data is never going to be 1, 0, 1, 0. It's going to be more noisy, but still it captures the idea. So if it's a 0.85, that's a 1. If it's a 0.05, it's a 0. If it's a 0.1, it's a 1. If it's a 0.15, it's a 0. Do you guys see that? That's basically what I'm doing here. This is the data that I'm going to use, and we need to train our model, okay? So let's go ahead and invoke the function generate real. Okay, so if I do generate real, if you notice, oh, I didn't run this. So you can see the vector there. 0.90, 0.01, 0.85, 0.10. That translates into 1, 0, 1, 0. That's my pattern that I want to learn, okay? That's the real data. So we have to think about the architectures that we're going to need. So we're going to use neural networks, right? But we need to build the architecture for the generative model and the architecture for the discriminator model. Now, for the discriminator, you already know how to do it because it's just a classifier, okay? So it's just a classifier and you know how to do it. The classic example that people talk about when they talk about GANs is the forger example. So you have a forger, and then you have a forger forging paintings, and then you have an expert that's saying if a painting is real or fake. That's the example. So there's two agents, the forger and the police officer or whatever, the detective, right? So the forger generates paintings, right? But you also have the real paintings, right? So there's the real Picasso, and then there's the forger's Picasso. And then the discriminator does what? The discriminator looks at a Picasso, the real Picasso, and it should say what? That's a real painting. Or it should look at the forged Picasso and it should say, no, that's a fake. And that's it. That's the game that we play, okay, with the GAN. So in this case, this vector here is the real Picasso, okay? But we're keeping it simple. If we wanted a real Picasso, it might be like 200 by 200, right? Spaghettify that vector. That would be what we would, the GAN would need to produce. But instead, we're just generating, to keep it simple, this tiny vector, okay? Any questions on that idea? All right. So that's the generate real. Then we can proceed over here. Okay. So now we're going to go here. And this is the function to generate a uniform random data. So here, this is going to generate a vector of size 4, but the values, it's going to pick them randomly. Okay, so that's the only difference. So now we can take a look by invoking our function generate random. And again, I should run this one first. And what do you see? I have a 55, that's a 1. I have a 0.12, that's a 0. I have a 0.07, that's a 0, and a 1. So I have 1, 0, 0, 1. That's just a random sequence, but that's not the sequence that we want. Okay, so just for a little bit of a contrast. Okay, so that's some data, basically. Now let's jump into the discriminator, because the discriminator is really the easiest to understand because you already know how to do classifiers. I'm going to create the discriminator class, and it's going to look so like everything else that we have been doing already with the object-oriented approach. And that's the beauty of this methodology, that it starts to pay off now. Okay, so let's go ahead and do just a label there so we know what we're looking at. Discriminator. And then I'm going to copy the class. So we can go over here. And it's similar, if not the exact same thing that we were doing last. All right, copied the whole thing. Okay, so I can run it. All right, so now let's discuss it, right? So as I said to you guys, in a GAN, you have now 2 neural networks, right? And they're basically they have different objectives, right? The discriminator needs to say true or false, fake or real. That's basically its goal. So the questions in your head might be like, okay, what's the data look like, right? You know, these are the things that you're thinking in your head. But let's break it down. So discriminator, notice it inherits NN module. The functions are still the same ones: init, forward, train, which we did last week, and then plot progress, which we also did last week, right? So you should know what these are already. Plot progress, if you look, we have a variable in init called self progress. We're just saving losses, okay? As we're training, remember, we want the losses to go down in the past. Here, though, with GANs, actually, we have a slightly different intuition of what we want with the losses, okay? So that's an important thing. So, but anyway, this function is the same one that I used last week. and it just plots the losses, okay? Then let's look at forward because it's an easy function. We've used forward many times before. What does it do? Basically, it takes in an input and predicts something, right? So because this is the discriminator, the input to it should be the paintings, right? The real paintings or the fake paintings. In our example, is the vectors of size 4, okay? All right. So that should be straightforward to you. Then over here, we're going to take a look at the training process or the training function. If you notice, just like before, it takes inputs and labels, right? Nothing has changed. Pretty much the same thing. We take an input through forward and predict outputs, right? Then what do we do with those outputs? We invoke the loss function and we compare the outputs to the targets, which are the real labels, and we calculate the loss, and then we would print it. Notice it's literally the same thing, okay? And then you guys should know already that we were just appending the losses into this self.progress variable so that we can plot it later, right? So that's basically, this is just for printing purposes, and it has nothing to do with the training. And then here is our very famous, very common by now, PyTorch does the heavy lifting, right? So we zero out the grads, then we calculate the gradients, right? Take the derivatives, right, of our loss function for our given W's, and then once we've taken all the gradients, optimizer.step updates the weights. Same thing as before, nothing changes at all. All right, so we've discussed progress, we've discussed train and forward. Those are the same. Here is where it might change a little bit, right? But it's very similar. Remember, the discriminator is just a classifier. So we can build classifiers that have an output layer of 2 neurons, or we have classifiers that have an output layer of 1 neuron. Since this is binary, it kind of makes sense to just have 1 neuron that is 0 or 1. So we're going to kind of assume if it's a 0, it's fake, let's say, and if it's a 1, it's not fake. True or false, right? So we decide what we want it to be. Does that make sense? All right. So let's take a look at it. So what are we doing here? Obviously, the super init, we've done this for weeks now. We just initialize the inherited class. Here's the architecture. I'll come back to it in a sec. The loss function, if you notice, is just MSE. And although this is a classification, you can use MSE. So, you know, no problem. Okay. The optimizer is stochastic gradient descent, or you could use atom. Notice self parameters, because this is a class, just refers to the weights and the biases of this architecture, right? So that should be clear to you now. That's still the same as before. Learning rate provided right there. And then here is just, we initialize our progress and our counter so we can keep track of the losses, etc. And print out the epoch and all. Got it? All right, so now the architecture is key here. So this should be an easy architecture, right? And familiar to you. It is 4 by 3 by 1. So is that deep learning or a multi-layer perceptron? Multi-layer, good. It only has one hidden layer. It can do nonlinearities because you have a hidden layer and you have activation functions, the sigmoid, right? So you should know this by now. All right. Why is it size 4? 4 represents the inputs, right? And what are the inputs? The vectors of 1, 0, 1, 0, right? So if we get 1, 0, 1, 0, that's like a real Picasso, right? That's what we want. And the other ones are the fake ones, okay? Got it? All right, so 4 is the vector size input. Y3, as you know, because you can pick that layer and you can make it 10. I mean, it works. And that's basically it. So this will work nicely. And then Y1, because as I said, it's the output neuron. We're doing a classification. So it uses a sigmoid also, if you notice. Sigmoid, no need for softmax because we only have 1 neuron. So then we have 0 or 1. Okay, and that's it. Super easy, right? All right. So that's basically the discriminator. That's done. And so far it's easy. Okay, now let's move on to the next part. So now we're going to train the discriminator with no generator. Okay. All right, so run it. All right, so now we're gonna invoke this class and just get a feel for how it works. Okay, so I'm gonna copy this code here. All right, and let's think about what's happening here. So I'm gonna start running it since it takes a bit. All right, so if you think about it, we test that the discriminator can separate between real data and random noise. Okay, so how do we do that? Obviously, we need to train the neural network, right? We need to train a classifier based on a neural network. So here I have my D discriminator. I'm gonna do 10,000 epochs, and notice that I invoke d.train, which is the training function. So if we go back to train, what does train take? Takes the inputs, which is the vector, right, of size 4, and the labels, right, whatever we want the labels to be. So we train it and we say, okay, if it's real data, 1010, then the label is 1. See that? It's true. That's the real object that we want the discriminator to find, right? And if it's fake data, then we give it the random data, which does not follow the pattern 1010, and we say that that is a 0. Does that make sense? So 1 gets the label 1, 1 gets the label 0. And this is how we train it. Got it? So that's it. It is trained now. It finished. So now let's go ahead and take a look at the loss function. Right, so if we look at the loss function, we can plot it easily. And there it is. And as you can see, the loss function did go down, right? So the model, basically, the weights became good enough that it recognized when it was a 1010, you know, it was saying it was a true and other ones, okay? And notice that the values were always different. They weren't always 1010. They were sometimes 0.80, you know, and so on and so on. But you can see the loss function going down there. So it is working, okay? All right, so we've done that. Now we want to test a discriminator on some dummy data. Okay, so let's comment here. All right, so now we are going to manually run the forward function. So notice that now D, the discriminator, has been trained on the data that I provided. And so I'm going to invoke, manually run the discriminator to check that it can tell real data from fake data, right? So D forward, if I give it generate real, which is a 1010, then it should predict what? 1, exactly. And if I give the discriminator, so D forward, generate random, what should it predict? 0. Do you guys understand? Because it should say that if it's a, you know, 0.8, 0.01, 0.90, 0.019, or 0.19, that's a 1010 pattern, so that's a 1 label, right? And if it doesn't follow that, then it's fake. Okay, so let's try out our device. And as you can see here, we've got that really nice thing about classification also, that it doesn't just provide the label, but also provides like almost like a approximation of a probability. right? So here it predicted 1, and this one predicted 0.34, which is closer to 0. Does that make sense? So we tested our discriminator, and that's kind of the discriminator, right? Now, where it gets a little bit hard is that now we have to create the architecture for the generator, and that's actually not difficult either. And then we have to train both of them together, and that can be confusing. Okay, that's going to be the part that you will probably have the challenge, right? But so those are the 2 points. Everything else should be pretty straightforward. So now let's go ahead and implement the generator architecture with our object-oriented approach. Okay, so generator network. Okay, there we go. And now I'm going to copy the generator class, which I have over here, which it still follows the exact same logic as before. All right, so let me run this one and then we can go back to it. All right, so we have our generator. Notice that this is the first time all semester that we've written some code where we have 2 neural networks. Okay, playing against each other. All right, so we have a generator, it inherits an end module. Once again, we have the function init. We have the function forward, just like before. We have a train function, which will now be a little bit different. And we have plot progress, which is the same thing as before. So plot progress plots the losses. Forward takes in an input and produces a fake Picasso, right? Now, the question in your mind right now should be, what's the input, right? This should be like the first thing that you've never thought about with a machine learning neural network. It was pretty obvious, right? What is the input here? Okay, then let's take a look at train also. This function. Notice the train has now changed a little bit. We do have inputs and targets, just like before, but now notice we pass the discriminator. We need to use the discriminator in the training of the generator. Okay? Because now they're playing a game. So for the first time, it's like you have in a very simplistic way, 2 AIs fighting against each other. And they're both trying to beat the other one, right? But that actually makes them better, right? And our ultimate goal is for the generator to be really good. All right, so let's go ahead then and take a look. So we got this idea of D here. Then we have the inputs, right? Which again, what is this input for the generator? Okay, what is it? So we feed in this input to forward, and that produces G output. G output of the generator is no longer a class. What is G output of the generator? The vector of size 4, or the Picasso, okay? So that G output, notice now, goes in to D dot forward. So the discriminator now needs to say something about what came out of the generator. Do you see that? So here is where the 2 neural nets are now facing each other. Okay, the generator gets an input, produces G output, a vector that of size 4. That vector goes into D forward, which produces D output. What is D output?
1
or 0, right?
Yeah.
The label. Yeah, the label. Very good, right? Very good. True or false. And then notice that the loss function, whereas before in the discriminator, what was the loss function? All semester, this was almost like a thing that we didn't even think about. We would just write that or cross entropy and done. But this time around in the generator, because the 2 agents are playing a game against each other, our loss function is actually based on the D discriminator loss. So we here will provide the output, what came out of discriminator, and we also have the real label. You see that? Oh, yeah.
The generator's loss is based off of how poorly the destructor does. I mean,
The-
the discriminator.
Yeah, it's based on the opinion of the discriminator.
Okay.
Let's just say that, right? So the learning process of the generator is based on the opinion of the discriminator.
So if the discriminator does good, the generator's loss is gonna be high. The generator's trying to make that a serial thing.
We'll see.
Okay.
But it's good. It's good. No, I like yeah, so good. But yeah, it's based on the discriminator. The discriminator just issues an opinion about the generator's output, okay? And that's our loss for the generator, which we also store in memory, right? So what is the objective of the discriminator? To be as good as possible in discriminating fake from real. But what is the objective of the generator? To be as good as possible in tricking the discriminator. Do you see that? The detective. It wants, if the generator makes a Picasso and the discriminator says it's not a Picasso, then what's the job of the generator? To play with the weights again, so that the next time the Picasso is even better. But it doesn't fool the discriminator. So then, once again, it adjusts the weights, and the next Picasso should be better and better and better until eventually it produces such a good fake Picasso that the discriminator cannot tell from the real one. Do you see that? They're both they both have a different objective, and it's very clever how you control it, okay? All right, so we got the losses there. Then this process is exactly the same as before. We just add the losses to progress. And then once again, as you are very familiar now, we zero out the gradients. We calculate the gradients. Then we calculate the derivatives, right? Calculate the gradients and in respect to the weights, and then update the weights in the neural network. Got it? This update is for the generator weights, of course. Got it? All right, so that's done. Plot progress is discussed. The train is discussed for the generator. Forward is discussed. Now let's zero in on init function, all right, which includes the architectural. Once again, we invoke init super so that we can initialize the inherited class. Here we just have our own counter and progress to keep track of the losses. And here is the optimizer, of course, that we're going to use to update the weights as usual, which can be stochastic gradient descent or atom, either one. Remember the parameters, these self-parameters are the weights and the biases, as we have done from the beginning of the semester. We plug them in here usually, and the learning rate, some value. Now, here comes the architecture of the GAN. This is the simplest, obviously. This could be a CNN-based architecture, and so could the discriminator. So CNN is not a thing that just exists in CNN code. Generator could have a CNN, okay? Keep that in mind, but that's just more complex. But the very basic here is that, let's look at this architecture. One layer of 1, followed by a layer of 3, followed by a layer of 4, okay? Notice that you have a hidden layer and you have activation functions, sigmoid, so you can do nonlinearities. The vector of size 4, because it's sigmoid here, can produce values 1, 0, from 0 to 1, right? That should be clear, right? It's producing the vector of 4. But initially, when we start this generator, it probably produces 1, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, right? There's just doing random things. As it's learning, though, the weights are being adjusted to the point that it predicts 1, 0, 1, 0. Got it? Make sense? Okay. The 3 is just whatever you want it to be in the hidden layer, right? You're the architect. And notice there's only one neuron in the input layer. And I still haven't defined what is this input. Now, this value could be 1, or it could be 10, or it could be 100. It doesn't matter. It's really whatever you need for it, okay? So the question is, what is it? as it turns out, the input is random. That's what you give again. Again, because a neural network needs input, right? But the input is just basically random data. To start from randomness towards non-randomness. The good way of thinking about this, maybe, although it's not exactly like that, is if you remember analog TVs back in the day. Maybe you've seen them on YouTube or something, right? So analog TVs had that staticky noise, you know, so imagine that that's how you start. And then from there, the picture starts to emerge. Although you don't really need the size of the output, right? If you notice, our output is 4, the input is 1. If we were doing MNIST, it would be, output would be 784, but our input does not need to be 784. It could be 100, for instance. It's you just need enough, a vector of a big enough size, but it's just random data. And that's just, again, because neural networks need some input. And the clever thing by Goodfellow and people like that is, yeah, let's just give it random data. It's like when you're learning, you start from an initial condition, which is some random vector, and you just update it over time. Got it? So that's the first key thing, or second key thing, that's different in the GAN, right? We saw that the loss is different, and now we see that the input is some random value. Any questions before we move on? All right. So let's go ahead and run this one. All right, so now we can test the generator output. So remember, it's a neural network already with random values, right? So in theory, it should generate a vector of size 4. It's just not a correct one. Okay, so let's go ahead and do this one here. Okay. All right, so we're gonna check the generator output, that it is of the right type and shape. So basically, if I was doing MNIST here, I would just want to see an image that is 28 by 28, basically. But really, it would be just static, like the static TV. Okay. Now notice here, 0.5 is just noise. It's just some random value that I'm plugging in there. Okay. So then I instantiate the generator, and then I'm gonna do g.forward. It needs an input, and it's just my vector of size 1 with some random value 0.5. This usually, it may require some experimenting as you're building a neural network, a GAN in particular. Okay, so let's go ahead and do that. And guess what? We're producing a vector of size 4. So that's like saying we're producing a Picasso. It's just not a good Picasso, right? There's no Picasso in it. In this case, we have 0, 1, 1, 1. That's what the pattern that it created. The neural network randomly now 0, 1, 1, 1. We need to train it so that eventually it produces 1, 0, 1, 0. Got it? Now, at the end of the day, when we're doing a GAN, we don't really care about the discriminator in general, although there may be applications where the discriminator is actually what you want, and you would use that separately. But remember, with a GAN, usually what you just want is a neural network that builds things, okay? So to give you the intuition, here we're going to train it with these vectors. Later, if we train it with MNIST, we would want a generator that randomly generates 7s or 3s or 5s or 1s, right? That's the idea. And then with the conditional GAN, you tack on an additional vector to the noise that actually gives it information, like saying, I want a 3, so then it's going to draw a 3. That's the conditional GAN. Okay, which the code is already on the GitHub. I just, I won't cover that today. Got it? All right, so the generator is generating, so that's good. The discriminator works. So now comes the hardest part. to visualize, and actually we're close to the end if you notice. We're almost done. So train the GAN. Train the GAN means training both the discriminator and the generator at the same time. Okay, so we're going to train our GAN, and we have to think about this one. It might take a little bit of thinking, retrospect, right, on your part to get this this part, because it's not obvious maybe. All right, so let's go ahead and run the code. Notice here that I'm going to run it because it does take a little bit. Okay, so what are we doing? So I added the time line of code. We've used this before just to tell us how long it takes to train. Doesn't take that long, I think. Then once again, we instantiate the discriminator and the generator, but now at the same time. Both neural networks are being enabled. This image list is basically a list because I'm going to produce vectors of size 4, right? I'm going to do 10,000 iterations. But every 1,000 iterations, I'm going to save the output of the generator. So I'm going to have basically 10 vectors of size 4. One at 1,000 epochs, one at 2,000 epochs, one at 3,000, and so on. So basically, initially, it'll be random sequences, but by the end, it should be what? 1, 0, 1, 0. You guys see that? And because we're actually generating decimal values, we can actually assign like a color, darkness to that value so that we can see that as epochs progress, it's getting more clear that it's a 1, 0, 1, 0. That's just for visualization. For those of you that like visualization, right? And so that's kind of the idea. That's what that's for. So notice all the magic happens here. It already finished, actually. So we do 1,000 epochs. Notice that there's basically 4 entries here, or 4 segments of code. The last one is the one I'll address first because it's the easiest to understand. Every 1,000 epochs, just run G forward, right? That's the generator. Give it our random noise. You see that there, our vector of random noise, and just detach it and append it to the list. That's what I was saying. That's the vector that we're collecting every 1,000 iterations. So we're going to have 10 of those so that we can visualize it later. So that should be straightforward. Now, here's the thing. There are 3 entries that are needed to train the GAN. Okay? We're doing 3 entries. Some of them should be straightforward. And then some might be, one of them might be a little bit difficult to visualize. At least for me, it's sometimes confusing. So train the discriminator, right? So we want to train the discriminator on true things. So detrain, generate real, label 1. So we're telling the discriminator, this is a real image by saying it's a label 1, and here's the image. So what's the equivalent of this if we were using a data set or MNIST? Here we would give it one of the images from MNIST. Okay, so data from the MNIST data set goes there, where generate real is. And we say to the discriminator, hey, that's label 1. Learn that this input to the discriminator should result in a 1. Okay? All right. Next step, we're going to do detrain. Notice now we do G forward, right? So G forward means that the generator is going to generate a fake vector, right? Because it's fake just means that the generator made it, right? So generator forward, once again, we have float here for the random vector, and the discriminator gets what? Label 0. So we're saying to the discriminator, this is fake. So that's straightforward also for the discriminator. It knows what's real, it knows what is fake. What comes out of the generator is fake, what comes out of the data set is real, 1 or 0. But at the same time, the third step is to train the generator. And the generator has a different objective. Okay? Yeah. What does the generator want? It wants that whenever it makes an image, the discriminator should say it's fake. Sorry, it's real. That's its objective. Do you guys, sorry, I messed that up. It's but that's the objective of the generator. The generator needs to generate an image and it needs to fool the discriminator. So the discriminator needs to say that it is a 1 because we've already established that a 1 is a real. Do you guys see that? That's it. It's literally just that. Right? So then notice, remember that the GAN function took D, right? Because it's based on what the discriminator thinks. So when we give it the real data to the discriminator, hey, that's a 1, that's real. When we give it a fake data to the discriminator, hey, that's a 0. We helped out, we did our job, the discriminator, we gave it the real things, right? The objectives. But on the other end, for the generator, when the generator is updating its weights, right? It needs to think, I think this is the best way of thinking about this. The discriminator has some weights, right? Sorry, the generator has some weights, right? And those weights generate an image that goes into the discriminator. And the discriminator says, no, that's fake. But that's not what the generator wants. The generator wants the discriminator to say, no, that's real. So it updates the weights again, generates an image, goes into the discriminator. The discriminator once again says it's fake, 0. And but that's not what we're telling it. We're telling it that it should say a 1. So what does it do? It updates the weights yet again, generates, goes into the discriminator. Now the discriminator says it's a 1. You fooled it. It says it's real because we've established that real is 1. So the objective of changing the weights is to changing them towards the label 1 of the discriminator. It wants to say that for the generator images, it wants to fool it. So it should say that they are real. It will only say that they are real when they're really good. In our case, when they are 1, 0, 1, 0. Does that make sense, guys? This is the part that hopefully that made sense. Think about it a little bit, but yeah, that's kind of what's going on there. And so now, if we take a look, we can print out the plot for the discriminator first. And if you look, this loss does not go down like regular losses, right? Initially, the discriminator loss went down, right? Like a regular one, but this one doesn't. Now let's take a look at the generator's loss. It's the same, right? Or similar. Why is that? You can interpret this idea as saying that you found a balance, okay? That you found a point, like an optimal point, where neither the generator nor the discriminator are better. But if you have one, like the discriminator loss going down like this, then probably you have a bad generator. So the generator will not generate good things. So this is kind of in the literature, you'll see this issue. It's a problem. So GANs are not exactly super easy to get to work. They need some tricks and things like that. Although for this and MNIS, it works perfectly fine and conditional, but you know, other things might be a little bit more challenging. Got it? All right, so now the last part, now that we have printed this, is to run a generator. So run the generator and predict. So now it's going to print out, you know, after a whole bunch of training, it needs to generate a Picasso. So what would you expect about this Picasso? That it's pretty good, or it starts to look like a Picasso. Remember, you give it this vector, random noise, basically, And then now, what did you get? 0.88, that's a 1. 0.06 is a 0. 0.91 is a 1. 0.05 is a 0. So the pattern is 1 0 1 0. Do you see that? So remember, this is like pretty powerful. A neural network. Not heuristic rules, just a straight up neural network. Learn how to make these patterns. And from here, it can make 7s, 8s, cats, all kinds of things. Okay? All right, so the last part is just to show you the progression. So let's go over here. Let's visualize the pattern of training. Control copy. Okay, and then the last part is just to plot it. Plot the 10 vectors of size 4. Okay, and there you have it. So how do we interpret this? If you look, the colors just represent, darker just means closer to 1, lighter just means closer to 0. So if you notice here, it's kind of like you're not very, it's almost like a 1 0 0 1, right? Basically. But notice that that's that iteration. So you have to look at them like this. So this is a vector of 4, and then there's 10 of them. So at iteration 3 or 4, it seems to still be 1 0 0 1. But about here, or here even, it's 1 0 1 0, and it's just becoming better and better. So it's darker here. So this is probably higher towards 1, and this lower towards 0. And that's a generative adversarial network, and that's how it works. That's it. Ian Goodfellow, 2014. Right, so the next step would be to take a look at, as I said, MNIST and then conditional GANs. So, but in the interest of covering all the topics, what I will do is we're going to take the 10-minute break. And then in the second half of today, I'm going to do transformers, right? Which is another generative model, way more complicated than GANs. Okay, so that's going to take, I'm going to do that in parts. But I'll start with some of the theory and intuition, and I have some code, and we'll talk about it. And that's actually, if we get to cover the transformer, then I'll be happy. All right, so yeah, so it's a good stopping point right now. It's 6:15. Let's take a 10-minute break until 6:25, and then we'll start the last topic for the semester. Maybe not the last lecture, but the last topic. So let me stop.